Alright, hey, I'm Yard, and I'm going to be showing you my circuit. It's bipolar multivibrator, essentially an analog flip-flop that is powered by an LED that will act as not only as the power source but as a light sensor in a way, because this multivibrator has sort of a minimum input voltage you need to make it function, which we can manipulate based on the amplification of our op amp. Alright, so let's show you the entire circuit. Alright, ignore this part. This is the voltage controlled oscillator last lab. The circuit is over here at the bottom, right here. So this is our first two subcircuits. It's hard to see because it's all in one chip, but we have the non-inverting amplifier and the inverting amplifier. And basically the non-inverting amplifier is just to increase the input voltage because, this LED right here, this acts as our input because LEDs, they emit light once a voltage is run across them, but the reverse is also true. If you shine light on an LED, a voltage will come across it, albeit very small voltage, which is why we need to amplify it. So this is our non-inverting amplifier. I used a 39K, 3.9K kilo ohm resistor and a 1 kilo ohm resistor to amplify this first input, and then over here we have the inverting amplifier. And essentially this is necessary because the since the diode is reversed, which is the only way for voltage to be across it, the output is going to be negative, so we have to invert it. And I just use a 4.7 kilo ohm resistor and a 2.2K resistor. So this is our input. The output should be a heavily amplified version of the input. And then this is fed into the bipolar multivibrator, which is essentially an analog flip-flop. Think of it as a square wave producer, because these LEDs will oscillate. When one is lit up, the other one isn't, and vice versa. So this entire circuit is useful because it, like a flip-flop, it stores information. It's like the lowest level, the most simplest form of information storage. And this is essentially the wire that connects the two together. And I'll be connecting that at the end. But for now, let me just show you the first subcircuit, which is the non-inverting amplifier. I already gave you a rundown, but now to test it, let's just go over here and let's get our channel 1, channel 2. Let's put channel 1 into the node with the LED, and then channel 2 at the first output of this operational amplifier, and this should give us an amplified version. So now we'll be moving over to Scopy. Alright, so now we're on Scopy. As you can see, we're using 5 volts for V plus real, negative 5 volts for V minus real. Let's enable them now. Now let's go to the oscilloscope. No light is on the LED right now, so you can see both input voltages, both channels are approximately 0. Just a reminder, channel 1, which is the orange channel, is connected to the node with the LED, which measures our input voltage, and channel 2 is connected to the output of the non-inverting amplifier. So now we're going to shine a light through it to see how the voltage across channel 2 increases. So as you can see, shining it closely now. As you can see, channel 1 is increasing, channel 2 is also increasing, but at a higher rate. And if we use the same input voltage as I used in the report, which is about negative 400 millivolts, let's see. Yeah. All right, that's about negative 400 millivolts. There we go. As you can see, it's close to 1.9, which is the value I calculated using the gain equation. More about that in the report. All right, so that's the amplified voltage, but it's not quite necessary. I mean, we could still amplify more, but we also need to invert it, which is only possible through an inverting amplifier. So now we're going to move channel 1 over to this output. Actually no, let's keep channel 1 into the input, and let's move channel 2 into the output of this inverting amplifier. Alright, and now I'll be showing you a Scopy graph. Alright, so we're on Scopy now. Let's turn on our V plus and minus rail. Let's go to the oscilloscope. Right, no light is on the LED now. As you can see, the voltages are about 0. But now let's shine a light. See it's slowly increasing. And then here you go. This is our maximum. It's about 2.9. And as you can see, while our input voltage is negative, because of this inverting amplifier, our output is now positive. And the reason it's 2.9 is because since the output is connected to this multi-bipolar, multi-vibrator, the output voltage isn't quite what the ideal case would be, which is in the report. But nonetheless, it's still sufficient enough to power the multi-vibrator. More info on that in the report as well. But as you can see, this is indeed inverted. Yep. Alright, that was our Scopy for that. So as you can see, it's amplified into a much higher voltage than the initial voltage by order of magnitude. That's basically necessary because, as I said before, this bipolar multi-vibrator over here, this only functions if the input voltage is high enough. And just talking about this third subcircuit over here, I use two 100 microfarad capacitors, two 33 kilo ohm resistors, and two NPN transistors, which essentially oscillates the LED into sort of like a square wave, where when one is on, the other is off, and it's not really increasing in magnitude. It's just, I mean, ideally it shouldn't, but in the Scopy graph that I'll be showing you shortly, it actually does increase, so it behaves more like a sawtooth wave. Right, so now, just for this third subcircuit, I'm not going to be connecting it to the output of the inverting op amp. I'm simply going to connect it to, oh whoops, this wire just broke. Give me 1 second to change this. Alright, so now we're at Scopy. We're going to be connecting, I just got a new wire and connected it to our power supply, so we can directly influence the voltage rather than relying on the light source, the voltage source of the LED. So let's just put in 3 volts, because that's what we recorded to be the approximate output voltage of the inverting amplifier. All right, now we can go to our oscilloscope. Here I connected each of the channels into each of the LEDs in this multi-vibrator. So let's see what the, as you can see, it's oscillating, but we can better convey this by increasing our time axes. Right now it's incredibly small, 1 microsecond. That's the for each box, for the grid, but if we increase it here, because it's blinking in intervals of about half a second. So if we increase it to 200 milliseconds, there you go. As you can see, this is what we should expect, because when one of the channels is high, the other should be low. That's what a flip-flop is. We can the measurements for period is in the report, but as you can see, this part of the subcircuit work. Now I'll use my phone to provide the light. All right, and now we just shine it over here, and there you go. That is our flip-flop behavior on 2 blue LEDs. And as you can see, if I remove the light, it's gone, but if I put the light back, it's there.